Modern data systems process millions of transactions per second. They exist in a harsh environment where traffic spikes and hardware failures are absolute certainties. Yet most engineering projects begin with a simple functional request. A product manager writes a ticket asking the team to build a dashboard that displays real-time market data to traders. To solve this, a developer connects a single client directly to a single database. Locally, it works perfectly. The functional requirement is met. But in production, under heavy concurrent load, that node crashes. Functionality tells you nothing about operational survival. Functional requirements provide a starting point, while leaving the burden of operational survival entirely to chance. Leaving operational reality to chance carries a measurable financial penalty. This stacked bar chart, based on research from the Software Engineering Institute, illustrates how 60 to 80% of all software development costs stem from rework and retrofitting. When you omit non-functional requirements, your system still possesses performance characteristics. They are simply unknown, untested, and waiting to be discovered catastrophically by your users. A developer focuses on building features for correctness. An enterprise architect focuses on engineering the boundaries and thresholds that keep those features alive. To make that transition, you must apply an active discovery framework before a single component is designed. VCSA. This stands for volume, constraints, SLAs and SLOs, and attributes. Mastering VCSA allows an engineer to move beyond basic features and design enterprise-grade systems. The process begins with constraints, design decisions that have already been made for you. Constraints are non-negotiable mandates that operate with 0 degrees of freedom. They form the strict physical boundary around your solution space. If your company mandates a specific cloud provider, or your budget is capped, or compliance requires local data residency, those factors dictate your tools before you draw a single line of architecture. Once the boundaries are set, you have to measure the internal pressure. This is volume. The structural difference between architecting a system for low traffic versus extreme traffic is absolute. A single monolith handles low loads perfectly. High volume demands horizontal scaling, asynchronous processing, and eventual consistency. You must immediately establish exact peak transactions per second and expected year-over-year data growth rates. Constraints lock the physical walls of the project. Volume dictates the sheer mass required within those walls. Next is the mathematical bedrock of system reliability: SLAs, SLOs, and SLIs. A service level indicator, or SLI, is a strict measurement of operational reality taken entirely from the user's perspective, like tracking exactly how long it takes a video to buffer. A service level objective, or SLO, is the target threshold for that measurement. It dictates how often that service must operate flawlessly. These percentages map directly to a strict error budget. This Google SRE outage math table shows exactly how much failure a given SLO permits. Look at the 99.9% row. This dictates your service is allowed exactly 43.2 minutes of total downtime per month. You cannot achieve this by simply deploying to one availability zone and hoping for the best. You also cannot assume that deploying identical instances in 2 zones guarantees safety, because shared global control planes and common failure domains will take down both systems simultaneously. This math enforces operational discipline. If your system consumes its allowed downtime, you freeze new feature development and allocate total engineering capacity to restoring reliability. The SLO provides the mathematical mandate that forces an architect to choose between a single server or a multi-zone automated failover. The final step is attributes. These are the abilities of software design: scalability, maintainability, portability. The danger here is designing in the dark. Without explicit definitions, teams rely on vague assumptions about what makes a system good, leaving critical performance and security requirements completely unstated. Capturing every dimension of quality requires a structured taxonomy. The ISO 25010 standard organizes system quality into 8 primary pillars. The performance efficiency pillar assigns concrete numbers, while the maintainability and security branches translate vague wishes into testable architectural drivers. ISO 25010 prevents omission. It ensures that every abstract business desire is translated into a measurable infrastructure decision. Let's apply this framework back to our opening functional requirement, displaying real-time market data to traders. A 200 millisecond latency SLO injects a content delivery network. A 10,000 user volume constraint shatters the database into read replicas. An ISO 25010 reliability attribute snaps a load balancer and message queue into place. Every component satisfies VCSA. While the functional requirement defines the initial intent, the quality attributes determine the physical structure of the system. This reveals the highest function of an enterprise architect: unearthing and managing non-requirements. Non-requirements are the tacit assumptions, the hidden dependencies, and the unwritten operational context that never make it into a product ticket. A well-designed system renders premature decisions deferrable. It isolates core business logic from the interlocking machinery of databases, frameworks, and deployment environments. Developers build features to ensure code correctness. Architects design structures to ensure system resilience. By utilizing the VCSA framework, you embrace the mathematical engineering of operational survival.